Chapter 1, Thin Lenses. Now, we have looked at the behavior of light rays when they fall on different types of surfaces. We started with plane mirrors in Form 1, and we saw when light rays fall on the surface of a plane mirror, they are reflected back at the same angle. The images are formed behind the mirror. They are virtual, same size as the object, and the same distance from the mirror as the object. Then in Form 2, we talked about reflection on curved mirrors, both concave and convex. And here, light rays either converge or diverge after reflection. And we saw the nature of images formed on these mirrors depends on the type of mirrors, whether concave or convex, as well as the position of the object, whether at infinity, beyond C, at C, between C and F, at F, or between F and P. And finally, in Form 3, we talked about refraction of light. And we saw when light rays propagate from one medium to another of different optical densities, their velocities change and in effect, they bend. In this chapter, we shall talk about the behavior of light rays on lenses. But first of all, what is a lens? A lens is a piece of transparent optical material with one or two curved surfaces to refract light rays. A lens may converge or diverge light rays to form an image. Reading glasses, binoculars, and optical instruments such as telescopes use lenses to enhance images of objects. In essence, a lens is just a glass slab, only that its surfaces are not flat but curved. Based on their shapes, lenses are of 5 types. A biconvex lens is one with a surface that is bulged outwards on both sides. It is generally referred to as a convex lens. A biconcave lens has 2 inward bent surfaces. It is generally referred to as a concave lens. A plano-convex lens has a convex surface on one side and a plane surface on the other. A plano-concave lens has a concave surface on one side and a plane surface on the other. And a concavo-convex lens has a concave surface on one side and a convex surface on the other. In this chapter, we shall only look at convex and concave lenses. Now, recall in Form 2, we saw that a curved mirror is simply a part of a sphere with the center, which we call the center of curvature, C. On their parts, lenses are formed by 2 parts of 2 spheres, so they have 2 centers of curvature. C1 is the center of curvature corresponding to the first curved surface, having a radius of curvature R1. And C2 is the center of curvature corresponding to the second curved surface, having a radius of curvature R2. A straight line joining C1 and C2 is the principal axis of the lens. Now, very so often, many students confuse between the behavior of light rays in lenses and the behavior of light rays in curved mirrors. But a simple way to remember this is that mirrors reflect light rays. In other words, light rays bounce off the mirror surfaces. On the other hand, lenses refract light. In other words, light rays pass through lenses, but they bend when emerging from the other side. If you recall in Form 3, we saw that when a ray of light enters a glass slab on the flat surface AB, it undergoes refraction and bends towards the normal. And as it emerges from the glass slab into air on the flat edge CD, it again gets refracted and bends away from the normal according to the laws of refraction. And because a lens is basically a curved glass slab, the same thing happens to light rays falling on lenses. A ray of light incident on a concave or convex lens undergoes refraction at each of the spherical surfaces. In the case of a convex lens, the light ray bends towards the normal C1N1 at the first surface, and then away from the normal C2N2 at the second interface as it exits the lens. Notice that a normal at any point on the surface of a lens is aligned through the center of curvature. Light rays parallel to the principal axis of a convex lens, upon refraction, converge at a point on the principal axis. This is called the second principal focus of the lens, f2. Principal focus towards the source of light is called the first principal focus of the lens, f1. In the case of a concave lens, the incident ray bends towards the normal C1N1 at the first interface, and away from the normal C2N2 at the second interface. When a parallel beam of light is incident on a concave lens, upon refraction, it appears to be diverging from a point on the principal axis, and such a point is called the second principal focus, f2. When we merely mention the principal focus, we are referring to f2. So let's look at the general terminologies, and we have already seen a few. The optical center O is a point on the principal axis of a lens such that any light ray passing through this point emerges undeviated. It is also known as the pole of the lens. The principal focus F is a point on the principal axis where a beam parallel to the principal axis after refraction converge in a convex lens or appear to diverge from in a concave lens. The principal focus occurs on both sides of the lens. It is also known as the focal point of the lens. In a convex lens, if an incident ray passes through a focus and its emergent ray passes parallel to the principal axis, then that focus is called the first principal focus, f1. If an incident ray passes parallel to the principal axis and its emergent ray converge at a focus, then that focus is the second principal focus, f2. In a concave lens, if an incident ray is directed towards a focus and its emergent ray passes parallel to the principal axis, that focus is the first principal focus, f1. If an incident ray passes parallel to the principal axis and its emergent ray appears to diverge from a focus, then that focus is the second principal focus, f2. The distance between the optic center and the focal point is called the focal length. Let's look at refraction on convex lenses. A lens in which both surfaces are convex is known as a convex lens. Light rays incident on a convex lens get converged at its focus. This is why a convex lens is also called a converging lens. When the sun's rays are converged at a point by these lenses, they produce enough heat to burn the object at this point of convergence. They are also used as magnifying glasses. Let's look at light rays propagated through convex lenses. When an incident ray passes through the center, it propagates undeviated. When the incident ray passes parallel to the principal axis, the emergent ray passes through the focus. When an incident ray passes through the focus of a convex lens, the emergent ray passes parallel to the principal axis. And therefore, we can find the position and the characteristics of images formed using convex lenses. And just like we did with curved mirrors, we draw two rays from the same point on the object, incident at different points on the lens, and find the point of intersection of the emergent rays. When an object is placed at infinity, the image is formed at f2. It is real, inverted, and highly diminished. When the object is placed beyond 2f1, the image is formed between f2 and 2f2. It is real, inverted, and diminished. When the object is placed at 2f1, the image is formed at 2f2. It is real, inverted, and of the same size as the object. For an object placed between f1 and 2f1, the image is formed beyond 2f2. It is real, inverted, and magnified. When the object is placed at f1, the image is formed at infinity. It is real, inverted, and highly magnified. When the object is placed between f1 and O, the emergent rays appear to be diverging. But if we extrapolate them backwards, we find the image is formed at f1 on the same side of the lens as the object. The image is virtual, erect, and magnified. Now, did you notice another difference between lenses and curved mirrors? If you haven't, watch here. This is a convex lens, but this is a convex mirror. A convex lens converges rays of light parallel to its principal axis and is therefore a converging lens. But a convex mirror diverges rays of light parallel to its principal axis and is therefore a diverging mirror. It is important to see that. So that now we talk about refraction on concave lenses. Now, a lens in which both surfaces are concave is known as a concave lens. That is, they form something like a cave. Light rays incident on a concave lens get diverged away from the principal axis of the lens. An image formed by a concave lens is always diminished due to the divergence of the rays. It is also known as a diverging lens. Let's look at light rays propagated through a concave lens. When an incident ray is parallel to the principal axis, the emergent ray appears to pass through the focus. When an incident ray passes through the optic center, it propagates undeviated. When an incident ray is directed towards the focus of a convex lens, the emergent ray passes parallel to the principal axis. And therefore, we can determine the position and the characteristics of images formed using concave lenses. Again, all we need are two rays from the same point on the object, incident differently on the lens. When an object is placed at infinity, the image is formed at f1. It is virtual, erect, and highly diminished. When the object is placed beyond 2f1, the image is formed between f1 and O. It is virtual, erect, and diminished. When the object is placed between O and f1, the image is formed between f1 and O. It is virtual, erect, and diminished. Again, notice the difference between lenses and curved mirrors here. This is a concave lens. It diverges light rays parallel to its principal axis and is therefore a diverging lens. but this is a concave mirror. It converges rays of light parallel to its principal axis, and it is therefore a converging mirror. Let's talk about linear magnification. Now, you can determine the size of the image of an object if you know the magnification of the lens. Magnification M is the ratio of the image size to the object size. It is also measured as the ratio of the image distance V to the object distance U. And this means that image size over the object size is equal to the image distance over the object distance. And therefore, magnification is equal to 1 if the image size is equal to the object size. It is greater than 1 if the image size is greater than the object size. And it is less than 1 if the image size is less than the object size. For example, an object 3 centimeters high is placed 8 centimeters from the optic center of a converging lens. If the image is formed 12 centimeters from the optic center, calculate the height of the image and hence the magnification of the lens. So we say h prime, the image height, over h, the object height, is equal to v over u. H prime over 3 is equal to 12 over 8. If we cross multiply, 8 times h1 is equal to 3 times 12. When we divide both sides by 8, we get h prime is equal to 4.5 centimeters. Magnification will be equal to h prime over h. That is the image height over the object height. That will be 4.5 over 3, giving us 1.5. Notice that magnification is a ratio of two similar units, and so it is unitless. Let's talk about the lens formula and the sign convention. Now, the lens formula defines the relationship between the focal length of a lens, f, the object distance from the optic center, u, and the image distance from the optic center, v. 1 over f is equal to 1 over v plus 1 over u. To denote the distance and the nature of image formed by a lens relative to the object, some conventions have been defined. All the distances are measured from the optic center of the lens. Distances measured in the direction of the incident light are taken as positive, while the distances measured in the direction opposite to that of the incident light are taken as negative. For example, an object is placed 12 centimeters in front of a convex lens of focal length 8 centimeters. Calculate the image distance and the magnification. Now, because it is a convex lens, the distances are positive. U is 12 centimeters and F is 8 centimeters, so we find V. We know 1 over F is equal to 1 over V plus 1 over U, meaning 1 over V is equal to 1 over F minus 1 over U. That will be 1 over 8 minus 1 over 12. The LCM of 8 and 12 is 24. 24 divided by 8 is 3, times 1 is 3, minus 24 divided by 12 is 2, times 1 is 2. So we have 1 over 24. And so 1 over V is equal to 1 over 24, meaning that V is equal to 24 centimeters. Magnification is given by V over U, that is 24 over 12, giving us 2. So, what is the relationship between magnification and the focal length? From the lens formula, 1 over f is equal to 1 over u plus 1 over v. If we multiply both sides by v, then we shall have v over f is equal to v over u plus v over v. V over v is equal to 1 and v over u is equal to magnification. So we shall have v over f is equal to m plus 1, meaning that v over f minus 1 is equal to m, or simply m is equal to v over f minus 1. From this equation, if we draw a graph of m against v, we shall have a straight line with a gradient of 1 over f. Next, we talk about determining the focal length of a converging lens. Now, we can use different methods to find the focal length of a converging lens. The simplest one, of course, is using a light box with parallel beams coming out of it, and all we do is put a converging lens, and where the beams converge is the focal point of the lens. But usually in schools, we perform elaborate experiments with repetitive procedures. So let's look at just two methods. The first one is by focusing a distant object. First, we locate some distant object outside the window like a tree and place a meter rule in the direction of the object. Then we place a convex lens in a lens stand along the meter rule such that the midpoint of its base is at the 5 centimeters mark. We place a white screen along the scale. We move the screen back and forth until a sharp image of the distant object is formed on it. Note the position of the screen on the meter rule. It's 19.3 centimeters. And that means the distance from the lens to the image is 19.3 minus 5, which is 14.3 centimeters. This is the image distance, which is also the focal length. Recall that light rays from infinity converge at the focal point. We repeat the experiment by placing the lens at the 10 centimeters mark, 15 centimeters mark, and the 20 centimeters mark. For the 10 centimeters mark, the image is formed at 24.2 centimeters. So the focal length is 24.2 minus 10, which is 14.2 centimeters. For the 15 centimeters mark, the image is focused at 29.4 centimeters. So the focal length is 29.4 minus 15, which is 14.4 centimeters. And for the 20 centimeters mark, the image is focused at 34.4 centimeters. So the focal length is 34.4 minus 20, which is 14.4. Then we calculate the average for the focal lengths. 14.3 plus 14.2 plus 14.4 plus 14.4 over 4, which gives us 14.4 centimeters. This is our estimated focal length of the lens. The second method is using an illuminated object, or what we call the UV method. We arrange a candle, a screen, and a convex lens as shown here. Adjust the position of the lens so that a blurred image of the candle is formed on the screen. Now move the screen back and forth until a sharp image is formed on the screen. Measure and record the distance between the candle and the lens, which is the object distance u, as well as the distance between the lens and the screen, which is the image distance v. Repeat the experiment for various object distances and record the image distances. Suppose we obtain a table like this one. From this data, we can find the focal length from the lens formula by two methods, either by calculation or by drawing a graph. Let's start with calculation. From the lens formula, 1 over f is equal to 1 over u plus 1 over v. If we simplify the right-hand side, 1 over u plus 1 over v, we shall have the LCM of u and v is u times v, or uv. UV divided by U is equal to V times 1 is V, plus UV divided by V is equal to U times 1 is U. And so 1 over F is equal to V plus U over UV. And if we find the reciprocals on both sides, 1 over F becomes F over 1 or just F, and the right-hand side becomes UV over V plus U. So F is equal to UV over V plus U. So on the table, we form another column for F equal to UV over V plus U and calculate the values. For the first row, we have 20 times 60 over 20 plus 60, which gives us 15. For the second row, 25 times 38 over 25 plus 38 gives us 15.1. Third row, 30 times 30 over 30 plus 30 gives us 15. And finally, the fourth row, 35 times 26 over 35 plus 26 gives us 14.9. Then we calculate the average value. 15 plus 15.1 plus 15 plus 14.9 divided by 4 gives us 15 centimeters. Let's try the second method, the graphical method. In this method, instead of calculating the value of F, we find the values of 1 over U and 1 over V. So in the first row, 1 over U is 1 over 20, which is equal to 0.05. In the second row, 1 over U is 1 over 25, which is equal to 0.04. Suppose we obtain a table like this one. Then we plot a graph of 1 over U against 1 over V. It will be a straight line cutting both axes. And from the length formula, 1 over F is equal to 1 over U plus 1 over V. If 1 over U is equal to 0, then 1 over F is equal to 1 over V. So at what point is 1 over U equal to 0? It's here at this intercept. So we read the value of 1 over V here. It's between 0.06 and 0.07. So let's say it's about 0.065. Also, if 1 over V is equal to 0, then 1 over F is equal to 1 over U. And 1 over V is 0 here at this intercept. So we read the value of 1 over U here. It's also 0.065. And therefore, the intercepts on both axes are equal to 1 over F. So 1 over F is equal to 0.065, meaning that F is equal to 1 over 0.065, giving us 15.38. That is about the same answer that we got earlier in calculation. So that now we move to power of lenses. Now, we know that light rays, when incident on a lens, converge in the case of convex lenses and diverge in the case of concave lenses. The degree of convergence or divergence depends on the focal length of the lens. If the focal length of a lens is small, then the convergence or divergence of light is more. On the other hand, if the focal length is large, then the convergence or divergence is less. The physical quantity, that is the measure of convergence or divergence of light introduced by a lens, is called its optical power. The optical power of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at a distance from the optical center. You know that a light ray, when incident parallel to the principal axis, after refraction by a convex lens, passes through the principal focus. If the ray is incident at a height h from the pole, and the deviation of the light ray, or the angle through which the light ray converges, is d, then tan d is equal to h over f. If h is equal to 1 unit, then tan d is equal to 1 over f. But from the definition, tan d is the power of the lens, and therefore optical power P is equal to 1 over f. That means optical power of a lens is the reciprocal of its focal length. The unit of power of a lens is the diopter with the symbol D. Remember, the focal length must be given in meters. So power of a lens is equal to 1 if the focal length is 1 meter. So for a lens of focal length 20 centimeters, power is equal to 1 over 0.2, which is 5 diopters. Power of lens can be positive or negative. As per the sign convention, focal length of a convex lens is positive and that of a concave lens is negative. And therefore, power of lens is positive for a converging lens and negative for a diverging lens. The focal length and hence the power of a lens depends on the medium in which the lens is placed due to differences in the refractive indices of different media. And so for a diverging lens of focal length 50 centimeters, power is equal to 1 over negative 0.5, which is negative 2 diopter. Next, let's talk about the applications of lenses. Now we can be able to see things that are extremely small or things that are far away from us with the help of lenses. For example, a magnifying glass. This simplest microscope is made from a single convex lens that bends or refracts light rays passing through it. It magnifies the object 5 to 10 times. However, microscopes used in schools and other laboratories are compound microscopes. They use at least 2 lenses to produce a magnified image. There is a lens above the object called the objective lens and another lens near the eye called the eyepiece or the ocular lens. Most compound microscopes can magnify objects by 10, 20, 40 or even 100 times. A compound microscope comprises of 2 convex lenses, the objective and the eyepiece. The objective lens has a small focal length and a small aperture, while the aperture of the eyepiece is larger. For an object AB placed at a distance just greater than the focal length of the objective f0, when light rays from the object are incident on the objective lens, the objective forms an image A'B', which is real, inverted, and magnified. This image then acts as the object for the eyepiece. If the position of the eyepiece is adjusted such that A'B' lies between the optical center and the first principal focus, then a virtual and magnified final image A'B', is formed. Next, the human eye. Now, just like artificial lenses refract light to create images, our eyes too have lenses that allow us to see things around us. At the very front of the eye is a transparent structure called the cornea that helps to focus incoming light. Behind the cornea is the iris. It has a circular opening called a pupil. The pupil expands or contracts depending on the amount of light entering the eye. Situated behind the pupil is a colorless, transparent, crystalline convex lens surrounded by the ciliary muscles. The muscles hold the lens in place and helps to change the focal length by adjusting the curvature of the lens. To view a distant object, the muscles relax, the lens becomes thin, and the focal length increases. To view a nearby object, the muscles contract, the lens becomes thick, and the focal length decreases. This ability to adjust its focal length is called the power of accommodation of the eye. The image formed by the eye is a real inverted image of the object that then strikes the retina. The light-sensitive cells of the retina convert the light into electric signals that are relayed to the brain. The brain converts these electric signals into an image. The minimum distance at which the eye can see objects clearly is called the near point, or the least distance of distinct vision. For a normal eye, it is about 25 centimeters. The farthest distance up to which the eye can see objects clearly is called the far point of the eye. In a normal eye, it is between 25 centimeters and infinity. The eyes can gradually lose their power of accommodation, resulting into blurred vision due to refractive defects. There are four main types of defects of vision. Hypermetropia, also called long-sightedness, is a defect in which nearby objects cannot be seen clearly. This is because the image is focused behind the retina. It happens due to increased focal length of the lens or decrease in the length of the eyeball. The defect can be corrected using a convex lens of suitable focal length. Myopia or short-sightedness is a defect in which distant objects cannot be seen clearly, and this is because the image is formed in front of the retina. This defect may be due to increase in the curvature of the lens or due to increased length of the eyeball. It can be corrected using concave lenses of suitable focal length. Presbyopia is an eye defect common in elderly people, where nearby objects cannot be seen clearly due to the increase in the distance of the near point. This may be due to the weakening of the ciliary muscles or due to decreased flexibility of the lens. It can be corrected using a convex lens of suitable focal length. Sometimes, both nearby and distant objects cannot be seen clearly, and this can be corrected using bifocal lenses. The upper part is concave, correcting distant vision, and the lower part is convex, correcting near vision. Finally, astigmatism is a problem where the image may be clearly focused on the retina in the horizontal plane but not in the vertical plane. This defect might be caused by an irregular curvature of the cornea or the lens. This can be corrected using glasses with cylindrical lenses.